Welcome learners. Today we are going to conclude the third chapter from the main textbook of Engineering Electromagnetics by William Haidt and John Buck, and we are going to talk about the remaining topic, that is on the divergence theorem and what is the del operator, and then we are going to look into one of the problem that explains how to find divergence or how to apply the divergence theorem, which contains this del operator as well. So we begin our discussion with the del operator. So this is the first thing that we want to understand. So the del operator is represented by this symbol. I am hoping that you have seen this symbol in your previous calculus class. So what is this symbol? This symbol basically is a vector operator, and the del operator is a vector operator, and it is nothing but similar to the partial derivation. So which means that del operator basically gives us variation along something. So it is going to talk about variation along something, means that we are talking about any axis system, with the basic being the rectangular coordinate system. So whenever any vector or scalar wants to make a certain movement or a small movement or a small variation, we can represent it mathematically with an operator or a tool known as a del operator. So a del operator is mathematically represented as such, where you can see that it is a vector quantity. How can we know it's a vector quantity? Because it has the unit vector along ax, ay and az, and the remaining elements are the variations or the motion along the x-axis, the y-axis and the z-axis. So this is the del operator's representation, that is similar to the divergence that we have seen in our previous lecture. So if it means that if I have any vector, let's say if I take the electric flux density vector d, I can represent it in its scalar and vector components. So it means it will be d of x along ax. So this is the scalar component and this is along a of x vector component. Then I can have d of y along a of y. Then I can have d of z along a of z. So this is the vector along with its component representation. And I know that if I want to take the divergence of this vector d, I can represent it as the partial derivative of dx along x. Then I can represent it as partial derivative of y, d of y, and then partial derivative of z, d of z. So this is what the divergence of this electric flux vector d looks like. So if you look at the del operator over here, and now we want to find the del operator's function on this electric flux d, so we can see it is the same thing. So you can see the expression which is shown over here. So now I'm taking the del operator and I'm doing the del operation or the dot operation on this vector d. So keep in mind, we are not doing the dot product. This is not the dot product, rather it is the dot operation, or in simple words, we are just multiplying the two elements. So you can see when we multiply the del operator with the electric flux density, so it is having the del operator operation, which is this value, and you are multiplying it with the component of vector d, having the scalar and vector notation. So you multiply the partial derivative of x with d of x, so the unit vector ax and ax becomes equal to 1, so you get the first term. Then you add the second term and you get the third term. So we can say that this operator del, when multiplied with any vector, in this case this vector is the electric flux density d, it is equal to the expression which we saw previously. That's why we can say it is equal to the divergence of d. So this expression as a whole is giving us the operation of the del operator with the electric flux, which is represented as divergence of d, and you can see that its output is a scalar quantity. So both of them were vector products or vector quantities, that was vector d and divergence or the symbol del operator, because it had the unit components ax, ay and az. But when you multiplied these elements together, the output of a del operator or a divergence is a scalar quantity. It is similar to saying that when we multiplied or we took the dot product of two vectors, we got a scalar at the output. It is the same thing. Similarly, if we have the del operator and we multiply it with a scalar quantity, the output will be what? It is going to be a vector quantity. So these are the properties of these divergences. So again, we have the del operator multiplied with the scalar quantity. So at the output, we are getting this expression, but this is a vector quantity because we have the unit vectors ax, ay, and az. So this is an important thing to keep in mind, that if we have an operation of a del operator with a scalar, the output will be a vector quantity. And if we have a del operation with a vector, the output will be a scalar quantity. So this is what we get for the del operator. Now we can use this del operator in the divergence theorem, or it is used with other elements as well. We will see in the upcoming chapters, that is, we are using the same del operator in the form of a gradient. Then we can use this as a curl operation as well, but for the time being we have just utilized it as a divergence property. So it's a mathematical tool which has many benefits. Now coming to the second topic, that what is divergence theorem. So this is the divergence theorem that we have. Let's look into the equation and then we'll see how did we reach to this equation. So the left hand side of the divergence theorem is basically the equation that we have seen, and that comes from the Gauss's law, that the electric flux density leaving any closed surface is the dot product with that small area that we have selected. And the right hand side of the divergence equation basically contains another element that we have seen just shortly, and that is the del operator getting multiplied with any vector. In this case, this vector is electric flux density d in a closed or a small amount of volume area that is represented by dv. So how did we reach to this divergence theorem, and what is the meaning of this divergence theorem? We are going to understand with this example over here. So first of all, how did we reach to the divergence theorem? So we already know what is a Gauss's theorem, or Gauss's law states that the electric flux passing through any closed surface is equal to the total charge enclosed by that surface. So again, we can see that this is the electric flux passing through any closed surface S, and if we take any small region, it is going to be equal to the total charge enclosed by that surface. And this expression can also be represented by, if we have any arbitrary closed surface, it is equal to the integral of the volume charge enclosed by that surface. What does it mean? We have previously seen that if we have any closed surface, any arbitrary surface, let this is any closed arbitrary surface, and if we have a point charge in this surface, a line charge in this surface, even if we have a sheet charge, these all three charges can be represented by a volume charge enclosed form as well. So this is a volume charge surface. So we can say that this point charge can exist inside this volume, line charge can also be a part of this volume, a sheet, let's say over here, can also be a part of this volume. So we say mathematically that all these three charges can be represented as an enclosed volume charge distribution, or it can be a part of the volume charge distribution. Thus we can say whatever the charge is being enclosed by this volume, whether it's a point charge, a line charge, or a surface charge, is going to be equal to the total electric flux that is leaving this surface. So let's say we know the electric flux leaving will be perpendicular to this surface everywhere. So this means that we can represent the electric flux that contains this charge also by the volume charge integral. Now this we have already talked about as well, and we have seen this mathematical representation visually over here. Now how does this volume charge relate to the final expression, or the fourth term in this equation? So this we have seen previously, that the equation over here is basically representing what? We can write this as divergence of D, as we saw previously, and from the first Maxwell's equation, divergence of D equals to the volume charge on that surface, or volume charge density. So we can say that if we have a volume charge represented as an integral, this portion can be replaced by the Maxwell's first equation, or Gauss's point law equation, that is equal to the divergence of D in the same volume. That's why the integral of the volume remains the same. So from this analysis or the Maxwell's equation, we are getting the fourth part of the equation. And if you look at the equation, divergence theorem then correlates that if we take the first part of the equation and the last part of the equation and we combine them or equate them, so we get the divergence theorem. So this is the divergence theorem. Now let us further understand what is the divergence theorem telling us. We have seen how we got the first and the fourth term from the main equation over here. Now what is the meaning of this divergence theorem? So first let's read this out. So the divergence theorem states that the total flux crossing through the closed surface. So what does it mean? This is the total flux which is crossing through this closed surface is equal to the integral of the divergence of the electric flux density throughout the enclosed volume. So this is equal to the integral of the divergence of the flux throughout this volume, or the integral dV. So what does it mean? So let us understand this through this closed surface. So what we have taken is, let us first understand the left hand side of this equation. So we have taken a closed surface. Here you can see this is a closed surface. We are representing or trying to represent it as a 3D closed surface. So this is the closed surface, represented as closed surface S. Now what the left hand side of the equation is saying, that the total flux crossing through the closed surface. So this means that whatever on the surface, any point on the surface that I am going to take, this is going to be the electric flux, and this is always going to be normal to this surface. So it is normal over here, it is normal over here, it is normal over here, it is normal over here. So this is the D that is crossing through the surface. So it is crossing the boundary of this surface. This is what the left hand side means. Now what else is given to us in this image? So you can see inside the surface we have these grid lines, or we can call this as a matrix, and these are the formations of the grid lines. So if I select any point on the grid line, let's say if I select this point inside this grid or this subsection or this small box, I can see immediately that the electric lines or the energy lines or the flux lines are originating from this. So we know that whenever energy lines are originating, mathematically it is basically the divergence. The energy is originating, so it is originating from point A inside this subsection, and it is going to other sections as well, as seen over here. Similarly, if I select any point, let's say I select this point B, so the divergence is the immediate release of the electric flux lines that is entering into other compartments as well. So I can say that this one portion, this one box, is I'm considering as a volume. So this is my V. Now from this, let us come to the right hand side of the equation. So the right hand side of the equation says that the divergence is enclosed in small boxes or small volume areas. So if I have any point A over here, so it is enclosed inside this small volume, and the field lines are moving away from this volume. If I come to this point B, I can see that the divergence or the lines are originating from these boxes and going or intersecting to the other boxes in the grid as well. So now if I want to find the effect of all these boxes, I can integrate it as a bigger integral. So it will become integration of V, which means I'm going to add this box, or the effect of charges in these boxes as a whole. So this means I'm taking the integral of all these small boxes. So how does it equate to the left hand side? So it means that if I have, let's say, this charge B, so I'll change the color. So let's say now if I have this charge B in this quadrant, and I know as per divergence it is having flux lines originating from here. Now some of the flux lines will enter its corresponding boxes with its volume or small volume dV, but some will cross the surface or the boundary over here. So we can see a few lines will cross the boundary over here. So it means that either I can integrate all these volumes to get the answer, or I can just integrate the field lines that are leaving the surface, and that will be D. So this is what the equation is saying. This is the relationship of the equation. So left hand side means if I just integrate the electric flux D coming out of the surface or coming out of the boundary, which will be easy because it will be a double integral, its answer will remain the same if I integrate the overall volume from these small boxes, that will be triple integral. So in case of integration, doing double integration in this scenario is easy than compared to the triple integration of a volume. So the equation or the divergence theorem gives us this flexibility that if I want to find, let's say, the effect of the charges in the form of divergence or flux lines, I can integrate it over a surface that will be the electric flux density, or that will involve double integral, or I can also do the triple integral by considering the overall volume, which is the combination of all the subsections over here. So this is what the theorem is telling us. We can even further understand it with a practical example. Again, this is the surface we just discussed, but let us say how we can understand the divergence theorem from our daily life. For example, take a water bottle, and now we see that there are certain leakages coming out from the water bottle, and we focus on one of the leakage. Let's say we focus ourselves on this leakage over here. So we say that this is the outer surface of the bottle where the leakage is, and inside we have this liquid. So divergence theorem says that either you take the closed surface and you find the double integral along the surface, whatever answer you get should be equal to the volume integral of the divergence of that charge. So it means that if I want to know that how much water is being coming out from the bottle, I can either focus myself on this leakage which is on the surface. So here I can directly find d dot ds as a surface integral. So it means I just need to integrate it twice to get the answer. The other option is that can be more complex, is I go inside the bottle and I select any specific point. Let's say I select this point A. Now I know in order to solve this integral which is inside the water bottle, I know that the amount of water that is coming towards point A is less than the amount or the effect of water that is leaving because of the leakage. So what I can do is I can apply the triple integral on this charge because it is the volume which is inside the water or inside the bottle. So this is also the possibility that is going to give me the answer, because now A is the point inside the water bottle where the divergence is the immediate effect the water is entering and leaving this surface. So this is how we can apply these two equations or these two portions of the divergence theorem to get the same answer. If you want the answer on the surface, you can apply the double integral. If you want the answer in terms of volumetric analysis, then you can apply the triple integral as shown over here. So in summary, divergence is basically the divergence of the flux density throughout the volume leads to the same result as the net flux of the closed surface. So this is what the divergence theorem is, and it depends upon the scenario, but we always go for the simplicity, which means that applying the surface integral, that is twice of the integral, is less complicated in terms of solving the problems than going towards the volume integral, which will be the divergence of charges inside the water bottle in this example. To better understand this, let us look at a problem and see how can we find the divergence. So in this problem, we have been asked to evaluate both sides of the divergence theorem. So what is the both sides of the divergence theorem? This one. So this is the main divergence theorem. So we need to evaluate the left hand side and the right hand side of the divergence theorem for the electric flux density D, and the object is a rectangular parallel pipe formed by the planes of x, y and z. So let us see how can we evaluate this, or we know that the answer for both the sides should be similar. So it's up to us which side we want to use, but for our understanding, as we have been asked to evaluate both the sides, so we are going to evaluate both the sides. So we know that the divergence theorem is given as, so we have the surface integral d dot ds is equal to volume integral of del operator with the electric flux, and it is in dV. So this is the equation number 1 that we want to evaluate. This is our left hand side of the equation, this is the right hand side of the equation. Okay, so keep in mind that this is a rectangular parallel pipe, which means we are in the rectangular coordinate system. where we know the coordinates are x, y and z, and the differential elements are dx, dy and dz. If it's a spherical or cylindrical, then our equations will change according to the x's values. For cylindrical it will be rho, phi, z, and for spherical it will be r, theta and phi. So let us stick to the rectangular coordinate systems as given in the question. So let us first draw the parallel piped with regards to these axes. So this is y, this is x, and this is z. So let me use this portion, and let's change the pointer since we are going towards a solution. So the parallel piped or a rectangular parallel piped will be such. So this is the, or let me first draw it and then I can color code it as per the planes provided. So the parallel piped is something like this. So it's a rectangular box where our object, this is our origin. Okay, this is our origin. Now let us highlight the relevant axes. So the planes is x is equal to 0 and 1. So when this is the origin and this is my x is equal to 0 plane. So x is equal to 0 plane would be this one from the origin at the back of it. So this is my x is equal to 0 plane. This is the back side of it, back side of the cube or the rectangular parallel piped. So if this is x is equal to 0, now where is x is equal to 1? So this is x equal to 1, the front side of this. So this is x is equal to 1 plane. So I know this is my a of x, this portion is my a of y, and the vertical is a of z. So let me use the correct arrow for the unit vector. So now I have figured out my planes for x. Now let's move to y plane. So let me use another color. So for y, we have y is equal to 0 and y is equal to 2. So y is equal to 0 means if this is the origin, this is my y is equal to 0 sheet. So I'm going to make it a bit bold. So this is y is equal to 0 plane, and this sheet over here, the right and left hand side from the origin. So this sheet over here is y is equal to 2 plane. Okay, again this is my origin which is at the back of the segment. Now the third is y is equal to, or this time we have let's take this green one. So now the third is at z is equal to 0 and z is equal to 3. So z is equal to 0 and z equals to 3. So so let's take this portion to be z is equal to 0. So let me try to draw this. This is my z. So this is my z. Let me call this z is equal to 0 plane, and since z is positive, so I'm taking the upper side. So this is my z is equal to 3 plane. So we have already seen this when we talked about the coaxial coordinate systems, but again for analysis I have done this. So this is all the axes or the planes for the rectangular parallel pipe. Now what we don't want to do is we want to start the analysis. So we start the analysis by first doing the let's start with the left hand side, which means I want to solve the surface integral first, d dot d of s. So this is what I want to solve. So I have been given the value of d which is in the question, but I first need to figure out d of s. So let's start with first d of s along the x-axis. So x-axis we are going to have two values for it. First at when x is equal to at the back side, and d of s along x for the front side. Back and front means that this is my origin, so this is at the back where unit vector will be a of x but with a negative sign, and when I move to the front it will be a of x with the positive sign. So this is the back and front. So this is my front and this is my back of the x-axis in terms of the unit vector. So since we are talking about the rectangular coordinate systems, its differential elements are dx, dy and dz. Since I'm moving in the back side, so I know that the face that is going to exist for the differential element will just be dy and dz, dx will not be there. So my dy, my ds of x backs will have the value of dy, dz, and the a unit vector will be minus a of x. So this is what I'm going to get. Similarly, for the front side, the variation will be along, or the faces will be along d and y, but the unit vector will be plus a of x, as we have seen over here. So this is the value of this. Now what is the value of d? So electric flux density, we know that the electric flux density can be represented in its components as dx along ax plus dy along ay plus dz along dz, a of z. So in the question we only have the x and the y component, so there is no dz component, so it is automatically be equal to 0. So our equation will have 2x y along a of x plus x square, and that's it, x square a along a of y. So this is the value of d. Now we just want to solve this integral, so I'll use this side. So the integral now on the left hand side, so I'll write it again over here. Left hand side, the integral is surface integral d dot d of s. Now we have the values for all the integrals, so we start first with the integral on the x-axis, and that is d of x, let me call it at 0. So this is my back, so I'm going to put it 0 over here, and this is 1. Okay, so 0 is back with d of s. Then I'm going to integrate closed surface, this is closed surface, dx of 1 along d of s. So then I can say that it is going to be the integral of x is equal to 0. So what is going to be d of x? So if I look over here in this equation, d of x is going to be the first element along a of x, and so I can write it like such. So 2x of y, a of x, I'm not going to integrate at the moment, I'm just inputting the value, dot what is d of s? So d of s back is dy d of z minus a of x, then plus the other value d of x, it is going to be 2xy of a of x with dy d of z with positive a of x. So now what we have done is basically we have looked into the value of d, which is electric flux density. So we know that it has a of x and this is a of x, so automatically it becomes minus 1. And when this equation comes to a of y, so we know that the dot product of a of y with a of x is equal to 0. That's why we haven't taken the second term of the electric flux density along ay. Similarly, for the next part of the equation, which is at x is equal to 1, so I can just say this is x is equal to 1 location and this is x is equal to 0. I haven't taken the second part because ax and ay will be equal to 0, so hence we'll be left with this ax and ax equals to 1. Now if you put the value of dx at x is equal to 0, this automatically becomes 0. So this term cancels out when x is taken as 0. Similarly, when I put x is equal to 1, I'm only left with this portion of the equation, or this portion. So I can say my left hand side, I will be left with double integral 2 of y, and because the value of x is 1, so I'm just left with 2 of y, and the values will be dy and d of z. Limitations for y and z is y is from 0 to 2, so this is integral is from 0 to 2, and z is from 0 to 3. So this is the integral that I'm getting. Now let us solve this integral over here, this one. So the integral for the left hand side comes out to be, I'm having a value of, so this is equation d dot d of s, where I've just taken the front side, and the value that I'm getting is integral for y and z, that is from 0 to 2 and 0 to 3, and the value is 2y dy and d of z. So now I can further solve the integral. 2 is a coefficient, so it will come outside. We can start with y and z, so I'm just going to put the values. So the y will be y square by 2 with limits 0 to 2, and z will be, so z is going to be a simple integral because we have no coefficient of z, it's just integral with dz, so it will be from 0 to 3. Then once we solve this, it comes out to be 2. You input the limits, so it will be 1 by 2 into 4 multiplied by 3, and the answer comes out to be 12. So this is the left hand side. Again, you can see that both the elements were vector quantities, but the output is a scalar term. So this is the answer to the left hand side of the equation. Now let's go to the right hand side of the equation and see, we should get the same answer. So for the right hand side, we now want to find what? We want to find the volume integral of the del operator with the divergence dv. So we know what is a del operator. It is nothing but the partial derivative of the vector, that is basically, or if we write the equation first, it can be a completion of the equation, but we just add the value of d with d of x plus partial derivative of the vector, which is d of y with y, partial derivative of d of z along z axis. So now what is the partial derivative of dx and dy and dz? So we look at the value of d. So the value of d, I'll write it over here so we can just figure out the value. So d is basically, so it is 2xy and plus x square. So the electric flux density that is given to us is 2xy along a of x plus x square along a of y. So this is the electric flux density given to us. Let's find the partial derivative along x. So we can see the value will be 2y, and then we have no component other than that. Then we go to the partial derivative of y. So along x, we will not take it, we will take it along y. There is no component of y, so it becomes 0, and z is not in the equation, which means that answer comes out to be 2 of y. So this is the partial derivative that we are getting for d. So now what is the equation? So we have figured out the partial derivative. Now we want to find dv. Now what is dv? So this is a rectangular coordinate system, so d will be the combination of all of these three elements. It means that our equation now is going to be multiplied with dv, which is basically, so the equation simplifies to 2 of y dx dy and d of z, and then we can take the integral of this equation. So the integral will be a triple integral because it's a volumetric integral. So this is for x, this is y, and this is z, and the values of x and y and z are from 0 to 1, 0 to 2, and 0 to 3. So this is from 0 to 1, 0 to 2, and from 0 to 3. So once you integrate the coefficients, it is going to be, so we can equate it over here. It comes out to be, so 2 is a coefficient, I'll take it outside. Now we start with x, since dx and integration is x, which limits from 0 to 1. Then you have y, so y is there, so it's going to be y square by 2 from 0 to 2, and then it is going to be z from 0 to 3. So once we solve this integral, we are going to get x is having a value of 1, y is going to be 2 square by 2, so this is going to be 1 by 2 into 4, and this is going to be 3. So this and this we can cancel out, so it is going to be 6 into 2, and this is again 12. Hence we have proved that whatever is the solution on the left hand side of the equation, as seen over here, is equal to the value on the right hand side of the equation. So this means that whenever we have a divergence theorem, we have the option to solve any portion of it, whether it can be a left hand side or a right hand side. It is going to give us the same answer. Depends upon the scenario, but we always stick to the one that has simpler integration to follow, and that is the left hand side, which is the surface charge distribution. And that concludes the third chapter from this main textbook.